Here we are, week 2, lecture 1. Today is the day that, it's the nominal day that assignment 1 is due. So your goal should be to get them done by start of class Tuesday so that you're ready for the next material. And I do have a grace period, though, so you have until Friday, end of day. And if you're doing it online, you can turn it up until midnight, but I don't want to encourage procrastination. And plus, you want to have fun on Friday nights.
No procrastination. I got a lot of stuff going on.
Yeah, I understand. Fridays I will be sort of out of here by 5, so you can slide under my door before that, but get it to me before I leave. And and so if you came in late, there's more handouts over there. Assignment 2 is due next week. Hopefully Tuesday you can get it in by. But again, there's a grace period every week, so you have until Friday, end of day, to get that in. And there was a question about extra credit. As I mentioned on Monday, you don't have to do all the problems in the assignment. Looking at an example, here is the assignment 2 handout. If you actually tally up all the points, there's more than 10 points here. You have 5 of these drill exercises, and then 2 of these assisted problem-solving exercises. That's 4, that's 9. And then you have, in this case, you have 2 of these 3-pointers, so that makes 15 points possible. I'm not going to give you 15 points if you do it all, so I expect you to work for free for some of that. But the way you can get extra credit, there's 2 things you have to do. You have to do 11 points of work at least, and you have to use the grader, so I don't have to look at your work really to grade it. So if you get 11 of those right, and I can just grade it really fast, then you get 11 points. If you don't use the grader, then the most you can get is 10 points. That's my way of encouraging you to use a grader, because it's really valuable for me. It saves me a lot of time. Josh?
Does that grace period extend to the grader also?
Yeah. Oh, yeah, so you have until Friday, end of day Friday.
To do that also?
Mm-hmm.
You have until Friday
to basically finalize your assignment. So I leave at 5 p.m. on Friday. It's due today so that you're ready for the next module, which we're going to start today. But I have a grace period until Friday. You can turn it in up until then without losing any points. And then after that, you'll start losing points.
Now, if you turn it online, do we have the system in the difficulty?
Yes. So the grader is basically ensuring that you have the correct answer. But then in order to keep you from copying somebody else's answers as yours into the grader, I need to see evidence that you actually worked the problems. And the evidence should sort of follow those guidelines of the problem-solving method that we showed you, so that it's not just an illegible scrawl. I should be able to read that and say, yeah, he worked through it. And that's how you get partial credit if your answers don't, are not all correct. So. So that's the shtick. That's the whole way it's sort of going to work. Does that make sense? Any other questions on that? I don't really have that in writing about the extra credit thing, or maybe I do somewhere. But who can find that stuff? Any other questions on the way the mechanics of the class is going to work? So today I'm recording this in Camtasia. I'm having some issues with the connecting thing. Today will probably be the day that somebody tries to log in from home during the class, and I can't, for some reason, I'm not able to connect properly, so I'm just aborting that. But the lecture recording will be posted still on. It won't be on CCC Confer, but it will be on 3C Media. I will post the video after class on that. So we're sticking with 3-dimensional vectors today. We're looking at 3D force vectors and also position vectors. And we have some, this really is nice because it really takes you to physical reality. This kind of stuff, is where the going to say, where the rubber meets the road, right? This is where we actually do stuff based on reality. So it gets you out of all those abstractions you're dealing with in math and physics and all. So a position vector, as you know, because I insist that you read the textbook before the lecture, as we talked about. I'm just kidding. A position vector is defined by, or is obtained by what? If we're calling it RPQ, how do we find that position vector? It's the coordinates of Q, right, the end point minus the coordinates of P. That's how you find the position vector. It's really just telling you how do you get to Q if you're starting at P. How far do you have to go in X, Y, and Z to go from P to Q? Does that make sense? So the answer to that is A. A force of magnitude F directed along a unit vector U would be given by what? Fu, right? No, I mean F parentheses U. Right? Right? Yeah, it would be F, the magnitude of F times a unit vector, right? That'll give you a force vector. Mm-hmm. Okay, so how does this help us in any way? Well, a lot of the structures that we're going to be dealing with are actually located in physical space. In fact, all of them are, right? And we need to know their orientation with respect to each other. So like the wing strut of an airplane, we could define the position. Well, and actually the forces are going to be acting along that vector. So we could define that position vector. It's an interesting process we're going to do today. We're going to find the position vector, turn it into a unit vector, you know, same direction, but a magnitude of 1. And then if we know the magnitude of the force, we can multiply it times the force vector. Now we've turned that geometry into a force vector acting along the direction of that strut. So it's an interesting process that we're going to be doing. Starting with the position vector. So this position vector is defined as a fixed vector that locates a point, one point in space relative to another point. So if we're talking about R here, this would also be called, if you notice how the arrow is going from A to B, we would call this RAB. It starts at A and it heads to B. Okay, and we can see that, and this sort of parallelogram prism, or whatever this thing is called, rectangular prism, it shows the journey from A to B along the X, Y, and Z directions, right? So we have to sort of go this far along the X-axis, we got to go this far along the Y-axis, and we got to go this far along the Z-axis. But these differences are really just the differences between the x-coordinate of B minus the x-coordinate of A, right? And the y-coordinate of B minus the y-coordinate of A. That's how far we go in Y. And for Z, we got to go the z-coordinate of B minus the z-coordinate of A. Those are the distances we have to travel in those three directions to do that. So the actual position vector we could write is defined as RAB is the xb minus xa times the I hat direction, yb minus ya times j, and zb minus za times k. That forms a three-dimensional vector. And B is the ending point, and A is the starting point. We always subtract the tail coordinates, the starting point, from the tip coordinates, which is the ending point of that vector. Now, in many cases, when we have like a rope or a thin beam of some sort, the force is going to be directed along the line of that material, whether it's a rope or a piece of wood or whatever. And so we can start with a position vector. And to represent it in Cartesian form, we would start with a position vector that really is closely linked to the geometry of the problem. This rope might be attached between point A and point B. And so if we want to define, and we know, say, that the rope is pulling on that bracket at A, with a certain force, we want to actually identify this force as a 3D vector. We know that force has to be acting along the line of action of that rope, which is attached between points A and point B, right? So the process is we first find the position vector to kind of figure out how you get from point A to point B. That's going to determine the direction of our force vector, right? Because when you pull on something with a rope, the force is acting along the line of action of that rope, right? So we first find that position vector. We turn that position vector into a unit vector by dividing by the magnitude, right? So RAB divided by its magnitude is going to give you a unit vector. That unit vector happens to be pointing in the same direction as the force vector. So all you got to do is take the magnitude of the force and multiply it times the unit vector, and now you've got a Cartesian force vector representing the force applied to that bracket at A. Okay? So kind of a three-step process that you got to do to compute that. So in our example today, we have a crane that's supporting a steel plate at 3 different points. And we are asked, or we are sort of told in our problem that there is a 400-pound force acting along the cable DA. And we want to find that force FDA in Cartesian vector form. Okay, so the process is going to be involving, first, we have a lot of geometry on this problem. And so we're first going to have to find this line connecting D to A, because we're told that the force is sort of acting along the cable. So the first thing we're going to do is we're going to find R dA. Okay, and the slow way, just to kind of show you how this works, is you can find the coordinates of point A. What are the coordinates of point A in this diagram? Yeah, it's located right up the z-axis, right? So x and y are 0, and the height of that is given on the diagram as 14. And point D is located at, it's a little bit harder. Yeah, 2 in x, right? We're going this way from the y-axis, 6 from the x-axis. And then it's got a height of 0, right?
Are you reading again?
Well, I'm looking at this diagram, and I have to figure out how far along the x-axis do we got to go. Well, there's this number here, 2 feet. You see how that's arrow? Yeah, it's really, it requires a lot of, visual sort of processing, right, to figure that out. You got to look at all the information. There's a lot of clues here, and they're laid out in such a way, you got to sort of follow that. You got to realize, well, this line is parallel to the x-axis, and we're going 2 feet down that line. Yeah. So, and then here, this 6 feet is telling you how far we are from the x-axis, right? That's in the direction of y. And then we're right on that place, so it has to be a height of 0. So RDA is A minus D. It's basically the tip, which is the end point, minus the tail, which is the start point. Okay, and so that means we subtract each of those coordinates. So we have 0, minus 2, so that means we're going to go minus 2i. You got to go 0 minus 6, that's minus 6j. And you got to go 14 minus 0, so that's plus 14k. Okay, that's RDA. Now, you don't have to always find A and D to do that. You're really trying to tell somebody, if you're starting off at D, how do you end up at A? How do you have to travel to end up at A? And you can sort of just see that, right? If you're starting at D, the way you're going to get to A is you're going to travel 2 units this way, 2 feet that way to get to the y-axis, and you're going to travel 6 feet that way to get to the origin. And then you're going to go up 14 feet, right, to get to A, right? Yeah, that's what it means. You're starting at D and you're going to A. So you got to go -2 in X, you got to go -6 in Y, and you got to go up 14 in Z. So you don't have to come up with those points initially if you're confused or if there's sometimes, these will be variables or something. There'll be like a point, this will be defined as like, PQR or something, right? And if it's an unknown, you have to use those variables, and then you can do that same kind of setup if you're going to use, you can use this this difference of the 2 point setups to do that if you need to. But in general, these are going to be numbers, and so you're just going to have to, follow the numbers to get to the end point from the start point. So the next step would be to find the unit vector dA, and to do that, we're going to find the magnitude of that position vector first, because then we'll find the unit vector by dividing. So the magnitude of RdA is going to be the Pythagorean, three-dimensional Pythagorean formula for the distance, right? We sort of went over that last week. Is everyone cool with this? It's -2 squared. It's the x value squared of that vector plus -6 squared plus 14 squared. And if you crank that out, you're going to get 15.36 feet. That's the length of the cable to get from D to A.
You said that's from D to A?
Mm-hmm.
From D to A.
Sorry? Yeah, it's the length of wire you have going from D to A. And yeah, so but our goal is we want to find a force vector, right? That force vector has a magnitude of 400 pounds. So what we're going to do is we're going to find the unit vector, UdA, and we're going to find that by dividing the position vector by its magnitude. So that's going to be -2 over 15.36I -6 over 15.36J, right, plus 14 over 15.36K. You see how that works? So U is just it's pointing in the same direction as that cable, but it only has a magnitude of 1. And our goal is to find a force vector to represent the force that's acting along that cable, which we're given the magnitude is 400 pounds, right? So we just say FU and we have our force vector. Right? So we find FdA, which is the magnitude of FdA times UdA.
So how come you didn't solve UdA?
I did. I just didn't, I didn't reduce it. I mean, these are the numbers for UdA, right? We'll save that for the end. So we're going to take the 400.
That's what that equals?
400 is this number right here. Yeah. Yeah, so that 400 is, because they're telling us in that diagram that, this is a force vector. It has a magnitude of 400 pounds, and it has a direction that's acting along the line of that cable, right? So that's why we had to start with a position vector first. Once we have the unit vector that's pointing in the direction of the cable, we just multiply that unit vector times 400. Now we got a force vector. So it's 400 times this thing. And you can write it a bunch of different ways, depending on how much symbols and letters and numbers you want to write. I could go back to my original RdA and just write, because it's a little bit easier, -2I minus 6J plus 14K, right, all divided by 15.36, right? And then I'm going to take and multiply that whole thing by 400. Everything in those curly braces is UdA. It's my unit vector, and I'm just multiplying that thing times 400. And when I do that and crank it through my calculator or whatever, I get that the force then would have to be minus 52.1 I minus 156J plus 365K. And what are the units of that? Is it newtons? Pounds, right? Okay, common sense check. Does that seem to be reasonable, that answer? And why? Does it seem reasonable? Why does it seem reasonable? It's oriented up, okay, which is good. And back towards the origin. And it's definitely, pointing more up than it is left or right, or x and y, right? And the numbers are about reasonable, right? It should have about a magnitude of 400, right? Does that look like it has a magnitude of 400? Because it has a component of 365, and, if you're not sure, you could crank it through that square root formula again, square those things, and take the square root of the sum, and then you should get 400.
So, you know they're reasonable because the way that force is pulling towards the x should be negative?
Yeah, you should have a negative x component, a negative y component, and a positive z component. And the magnitude should be about 400. If you take those components, square them, add them together, take the square root, you should get about 400. Well, you should get exactly 400.
I don't see how the x component should be negative.
Yeah, why do you think that, who can explain why the x component is negative?
Like A is at the origin, so it's like getting pulled.
The attachment point of B is in positive x.
Yeah, so you're going to the left of the x-axis.
Yeah.
Towards negative.
It's like
Going
relative
backwards.
from yeah, it's like we're with respect to D almost. Like they're
So like when you start at D, you're at a bigger x value than when you end at D. Okay. Well, at the end of the course.
I know, does that help? All right, here's another thing. If we look at this vector and we try to project its components, right? You're going to sort of see that can you see this now, where the x component is going to sort of have to be pointing that way, isn't it? Oh, he's getting help from somebody else too. Okay, let's all help Noah at the same time. Yeah. So we found the force in Cartesian form. Now we're going to see the answer again in typewritten form. So you can see how they did it. See, and this is how basically you'll normally do it. The figure shows that when relating D to A, we will have to go minus 2 feet in the x direction, minus 6 in the y, and 14 in the z, right? So you can basically read the position vector right off the chart. It's not that hard, right? And we find, it does say you can also find it by subtracting those coordinates if you want. But then you find the magnitude, you find UDA, you divide, and then you find FDA by 400 times UDA, and you're good. Okay, that wasn't so hard, was it? Well, try this out. If P and Q are 2 points in 3D space, how are the position vectors RPQ and RQP related? They're negatives of each other, right? Yeah, you would take them multiplied by -1 to get from one to the other. So the answer is C. And if F and R are force vectors and position vectors respectively, what are the units of R times F over F? These are SI units, so we would be A.
So R is distance, C. So R is distance and then F is the force, right?
R is distance, F is the force. we'd be dealing with distances, right? Because the F units cancel, right? Because you got the force vector divided by its magnitude. So that this would become a unit vector as well, which is dimensionless. And then you're multiplying it times r, which has a unit of meters if it's an SI system, so the answer should be C.
If we didn't have divided by F, it would have been D.
Yes, and in fact, we are going to sort of be doing units like that when we do cross products and torques and stuff. So that is going to come later. Okay, and I think this is on the back side of the handout where you have another problem here. Two forces acting on a pipe. And we actually are asked to find the magnitude and coordinate direction angles of the resultant force. So this one's going to be a lot of work because we got to find two vectors. In fact, we might not even have time for it all, but let's give it a shot. Crank it through. Okay, we have two forces, so we have to find these forces in Cartesian form, right? Then add them together, and then find the magnitude and the coordinate direction angles of that resultant force, of the sum of these two forces added together, which is the net force acting at C on that post, right? So for one, we're going to, step one, let's find F1 in Cartesian form. And F1 is given in what style of presentation are we given the that vector? Are those direction angles or projection angles? Projection angles, right? And because it's a little strange here, let's determine these points A and C and then find it that way. So point A is a projection angle problem. We've got to figure out what's the x position of point A. Yeah, actually, nicely, we're given sort of the direction here and the distance here, and this would sort of be like the r prime of this vector, is 3 feet to go from the origin to A. So the x position is going to be 3 times what? It's the sine, right? Because we want the opposite angle, right? Not the adjacent angle. That's the distance in x, and it's minus, isn't it? Minus 3 sine of 40, isn't it? And the y is going to be what? 3 cosine of 40, and z is 0, right? And c is pretty easy. That's just 0, 0, 4, right? Those are the geometric locations of where the rope is tied. Okay. And, yes?
So, for the first one, we get negative 3 sine 40.
Uh-huh.
That's because we're given that projection angle, right? So,
Yeah.
the negative again, can you explain that?
Oh, the negative, again, because looking at the orientation of the diagram, this x, we're trying to find the location of A and C to find the position vector RCA. And the diagram shows the direction of the positive x-axis is going this way, but our cable here at A is attached in the negative x direction, so that's why we put a minus in there.
But, like, how did you figure out it was sine instead of cosine?
Well, because if you look at this sort of head, from straight up, where you're looking right down the z-axis, you've got the y-axis going here, you got the x-axis going here. You're told this is 40 degrees, and we need to know this distance right here. Which is the same as this distance here, which is 3 sine of 40, and it's negative because we're going in the opposite direction of the x-axis. Right. These kind of mental, rotations and stuff are really helpful Which is why it's helpful to take engineering graphics. If you had engineering graphics, you're going to be able to do all that kind of stuff really well. If you haven't had engineering graphics, it's okay. You'll get it in this class, and then you'll be more prepared for engineering graphics. So RCA is A minus C, right? So that's going to be, minus 3 sine 40 I plus 3 cosine 40 J minus 4K, right? That's if we're starting at C and we're heading to A, right? We got to go negative X direction. We got to go positive Y direction. We got to go negative Z to go from C to A. And the magnitude of RCA is, turns out, if you do the math, it's just 5. It's a 3, 4, 5 triangle. You can do that if you do the square root of the square of those components as well, added together. So therefore, F1 is 100, because we know it has a magnitude of 100, times the position vector RCA divided by its magnitude, which is 5. This whole thing here is, that is UCA, right? And cranking that through, you're going to get minus 38.57I plus 45.96J minus 80K. Okay, we just finished F1. Now we got to find F2. So for F2, we got to go from C to B. And another way we can do this, we say, well, we know F2 is going to be 81, right, times RCB divided by the magnitude of that. And this kind of shows you how you can sometimes just sort of write these things out. It's not really that hard in general. So we take 81, we multiply it by, and now what's RCB? Again, we're starting at C, and we're headed to B. How far in X do we got to go? Yep. So it's 4I. How far in Y do we got to go? Minus 7J, right? And how far in Z do we got to go? Minus 4K. And if you do the Pythagorean thing, the magnitude of that thing just happens to be 9. Sometimes the numbers work out pretty well. I'm just going to write that. It's divided by 9. You can work that out. So square root of 16 plus 49 plus 16 turns out to be, that's, 49 plus 32 is 81. Square root of 81 is 9, right? Good?
I'm curious about divided by 9.
Yeah, so that 9, basically, I'll just say that 9 is the square root of 4 squared plus 7 squared plus 4 squared, right? Sometimes they choose these things so they're nice, neat numbers. Which helps speed up the process considerably. So then our resultant is just F1 plus F2. And kind of cutting to the chase, it works out to be minus 2.57. Again, you can sort of tell, it's, the x component of F2 is going to be 81 over 9. That's 9 times 4 is 36, right? And we're going to add to that minus 38.57 from the F1. giving us minus 2.57 in the I direction. Oh, actually, sorry, I missed a step. Sorry, I shouldn't do that. I'm deprive you of that. There is a nice, I did consolidate F2. F2 turns out to be 36I minus 63J minus 36K. So adding all those pieces together, the individual components F1 and F2 added together, gives you this final resultant vector minus 2.57I minus 17.04J minus 116K. Again, the magnitude is found by summing the square of all those terms, right? Just to kind of simplify things, I'm not going to write out all those numbers. Again, it turns out to be a really nice number. It's just 117. I guess that's, I don't know if that's exact or not. There could be a fourth digit there. I might have just rounded it to 3. You got 0.27? Okay.
And that's the magnitude for the answer.
Yeah, that's the magnitude of the resultant.
And then how do we figure out the direction?
Yeah, the direction angles are pretty easy, because once you have the magnitude, alpha is just the inverse cosine of the x component divided by the magnitude, so minus 2.57 over 117.3, which should be around 91.3 degrees. Yes, and beta is always the cosine inverse of the y component over the magnitude. Mm-hmm.
But that's when you add them together. Right?
No, this is the direction angle formula, right? If you know the Cartesian components and the magnitude, the direction angles are just taking each component, dividing it by the magnitude, and taking the inverse cosine.
No, I'm talking about the negative 2.57 and the negative 17.4. That's adding the two forces together. That's how you get the angle.
No, well, this 2.57 is the addition of 36I from F2 and minus 38.57I from F1, right? And then but now we just have this, and the same, for the y and the z. And now we just have this resultant vector, but we're asked to find what's the direction of that resultant vector. And so we're going to find the direction angles by taking each component in turn and dividing it by its magnitude of the magnitude of the whole vector.
And it's always inverse cosine.
And that's always the inverse cosine, yeah. Notice gamma is the inverse cosine of minus 116 over 117, which is pretty close to 180 degrees.
Is it also, just for clarification, cosine alpha beta and gamma squared equals 1?
Cosine squared alpha plus cosine squared beta plus cosine squared gamma has to equal 1, yep. Mm-hmm. Yeah, it's another way to kind of check, but they will automatically if you do it this way.
Right.
Mm-hmm.
So anytime you have, the magnitude and then the xy components, you plug it in like that and get alpha beta again.
Yeah. Mm-hmm. Yeah, it's real easy to get the direction angles from a vector. Very easy. And again, these slides also show you how to do it a slightly different way, a little more compact. Kind of cranking through the same thing there, giving you the same answer. So common sense, what is that telling us with these direction angles, by the way? So does that help you visualize how that force is oriented with those direction angles? So when alpha is 90 degrees, that means the resultant is 90 degrees away from the x-axis. It's sort of trying to figure that out. And beta is 98.4, so it's, I don't know, I'm not really getting it, are you? But 172 means it's almost pointing sort of straight down, which is kind of makes sense because those ropes are kind of opposed, and it kind of looks like it looks like the resultant is kind of coming down something like that. Do you agree? Something like that. Okay. Are you ready for the attention quiz?
Yes. Tell me there's going to be a quiz today.
There's a quiz every day. Attention quiz. 2 points. Have coordinates. 1, 2, 3, and 4, 5, 6. The position vector is given by what?
B.
Our QP means we're starting at Q when we're heading to P, right? Going minus 3 in X, minus 3 in Y, and minus 3 in Z, right?
When you do QP together, you're just subtracting them?
Yeah, you're always subtracting the initial from the final. So it's P minus Q, right? We're starting at Q.
Minus initial?
Huh?
Final minus initial?
Did I say that? Yeah, final minus initial. You're starting at Q and you're ending up at P. So it's 1 minus 4.
No, I think you said initial subtracted from
Yeah.
like what?
Yeah, sometimes I'm not even aware of what I'm saying. The force vector, F, directed along a line PQ, is given by what? C.
We're red are vectors, right?
I agree. Yeah, red are vectors. I concur. That is it. We finished early, which is good because I have to go to a meeting at 2. And I have to print out some stuff. So get out of here, you guys. I'll see you tomorrow. Don't ask me any questions today.
So, Tom, submit answers today and then bring the sheet tomorrow?
Bring your your work solutions tomorrow. Yep.
Or till Friday, right?
Yep. Perfect. Thank you. Right here. Yep.
Thank you.
Thank you.